On the conceptual distinction between particles and waves and its implications in quantum theory. Abstract. The distinction between particles and waves has historically constituted a foundational element in physical theory. However, the development of quantum mechanics introduced the concept of wave-particle duality, challenging the classical separation between these categories. This paper revisits the fundamental definitions and properties of particles and waves, emphasizing their conceptual and physical differences in terms of spatial localization and mechanisms of energy transmission. It further examines the historical evolution of wave-based interpretations, from early ether theories to modern quantum mechanics, and critically analyzes the extension of wave properties to subatomic particles. While the quantum formalism has proven highly successful in predictive terms, this work highlights ongoing interpretative tensions regarding the physical meaning of wave-particle duality and calls for continued scrutiny of its conceptual foundations. 1. Introduction. The classification of physical phenomena relies on clearly defined conceptual categories and the consistent application of their associated properties. In classical physics, particles and waves represent two fundamentally distinct modes of description. Particles are typically regarded as localized entities with well-defined positions and trajectories, whereas waves are extended phenomena characterized by oscillatory behavior within a medium or field. The emergence of quantum mechanics in the early 20th century introduced a unifying framework in which these categories are no longer mutually exclusive. The concept of wave-particle duality suggests that subatomic entities may exhibit both particle-like and wave-like properties, depending on the experimental context. While this framework has achieved remarkable empirical success, it also raises significant conceptual questions regarding the nature of physical reality. This paper aims to revisit the foundational distinctions between particles and waves and to examine the historical and theoretical developments that led to their unification within quantum theory. 2. Definitions and fundamental properties. 2.1 Particles. A subatomic particle may be defined as a highly localized, discrete, and autonomous unit of matter. Such entities are typically associated with extremely small spatial scales, on the order 10⁻⁻30 cubic meters or smaller. A defining characteristic of particles is their capacity for translational motion, enabling them to transfer kinetic energy through displacement. 2.2 Waves. A wave is an oscillatory phenomenon that arises within a field or medium when subjected to a perturbation. This oscillation may occur in various physical systems, including electromagnetic fields, gravitational fields, and material media such as gases, liquids, and solids. Unlike particles, waves are inherently extended in space and do not correspond to localized objects. 2.3 Key differences. Two primary distinctions can be identified. Spatial characteristics. Particles are localized, whereas waves are spatially extended and may occupy large regions of space. Experimental observations, such as interference patterns in slit experiments, demonstrate that wave-like phenomena can manifest over macroscopic distances. Energy transmission. Particles transmit energy through translational motion. In contrast, waves transmit energy via oscillatory processes within a medium or field, without requiring net displacement of the underlying substance. These differences suggest that particles and waves represent fundamentally distinct physical descriptions. 3. Historical development of wave-based descriptions. 3.1 Early wave theories of light. In the late 17th century, Christian Huygens proposed that light propagates as a wave through a hypothetical medium known as the ether. This concept provided a framework for understanding optical phenomena such as reflection and refraction. 3.2 The Michelson-Morley experiment. The Michelson-Morley experiment, 1887, sought to detect the motion of the Earth through the ether. Its null result was widely interpreted as evidence against the existence of such a medium, leading to the abandonment of ether-based models. 3.3 Emergence of wave-particle duality. In 1924, Louis de Broglie introduced the hypothesis that matter possesses wave-like properties, establishing a relation between a particle's momentum and its associated wavelength. This idea was later incorporated into the formalism of quantum mechanics, where physical systems are described by wave functions encoding probabilistic information. 4. Conceptual implications in quantum mechanics. Quantum mechanics extends wave-like concepts, such as interference, superposition, and wave function collapse, to systems traditionally regarded as particles. This has led to a hybrid descriptive framework in which subatomic entities exhibit both localized and delocalized characteristics. While this approach has been experimentally validated, it raises important interpretative issues. In particular, it remains an open question whether wave-particle duality reflects an intrinsic property of physical systems or arises from the mathematical formalism used to describe them. At macroscopic scales, classical distinctions between particles and waves remain operationally valid. The apparent breakdown of these distinctions at the quantum level therefore continues to motivate foundational investigations into the nature of physical reality. 5. Discussion. The unification of particle and wave descriptions represents one of the most profound conceptual shifts in the history of physics. However, this synthesis may also obscure important differences between these categories. By re-examining their defining properties, it becomes possible to clarify the limits of their applicability and to identify potential sources of conceptual tension within current theoretical frameworks. Further work is needed to determine whether alternative interpretations or models may provide a more coherent account of the relationship between localized and extended physical phenomena. 6. Conclusion. Particles and waves possess distinct physical and conceptual characteristics, particularly with respect to spatial localization and mechanisms of energy transfer. Although quantum mechanics successfully integrates these descriptions into a unified formalism, the interpretation of this unification remains a subject of ongoing debate. A careful reassessment of the foundational assumptions underlying wave-particle duality may contribute to a deeper understanding of the structure of physical theory and the nature of reality.